this video, we are going to focus a lot on graphical analysis. Now, even though this video is for the velocity, distance, displacement, acceleration unit, the skills I'm about to teach you now is something that we'll be practicing throughout the entire year. Now, some of you might be in calculus, and in calculus, you'll be practicing the same skills that we are going to be doing today. So, without further ado, let's begin. Now, on the screen before you, you can see the same function that we used in the last video. This is the position of an object, 2t squared plus 3. This is just an object that is moving. And in the previous video, we found that at position 1 second, we were at position 5 meters, and I believe we looked at position at 3 seconds. It was like 21 meters, right? And we found that the delta t, the change in time from 1 second to 3 seconds, was 2 seconds. Therefore, the v average, we found it to be 21 minus 5, all divided by 2. So this would be 8 meters per second, and we just said it was positive, and so we're just gonna put that in there. It's to the right. Okay, so that was the mathematical approach to this function, and we found the average velocity. So that's good and all, but a lot of the problems that you'll see will be in the forms of a graph. So let's create a quick sketch of what this graph might look like. So I'm going to create a y-axis and an x-axis. I'll put the x-axis a little bit below. There we go. You can also plug this into your graphing calculator to see what this function looks like. Now, I'm going to be focusing mainly in the first quadrant. That's because our y-axis is position. Okay, so good graphing skills, make sure you have your variable. And in this case, our variable is position, and our units, and in this case, it's meters. Okay, and then the x-axis, we have time in seconds. All right. And the reason why we're going to focus mainly in the first quadrant is because we can't go back in time, right? We can't have negative time. And so we're going to focus on the first quadrant there. Now I'm going to do a quick sketch, and when you do this sketch, just try to fill in that first quadrant to the best of your ability. Okay. And voila. So that looks like 2t squared plus 3. All right. Now, let's go back to this average velocity of 8 meters per second. So from this graph, what we can do is we can take a look at the 1 second mark, right? So we're just going to say right here, this was the 1 second mark. And then we're going to look at the 3 second mark. We'll just say, let's say right around here. Okay, right around here is the 3 second mark. And I encourage you to do the same, right? Put the 1 second mark a little closer to the y-axis and the 3 second mark a little further back. All right. So what we're doing here is we are trying to see graphically how can we tell the average velocity from the graph alone, right? Yes, we have this formula, but how can we tell from the graph? So let's break this apart. We're going to do a quick little side note. And so this is where we have the year-long skills. I'm going to do this in a different ink so that kind of stands out, right? So here we have our y-axis, and here we have our x-axis. Okay, not to be confused with position. So if we take a look at the average velocity formula, right, we have delta x over delta t. So change in position over change in time. Now, the change in position, this is as if we are saying the change in the y-axis over the change in the x-axis. Okay. Once again, I'm going to highlight that this is the y-axis here I'm talking about, and this x-axis is here. Okay. We're not talking about the variables, because as a quick reminder, that variable is position and this variable is time, but this x here represents the axis. Okay, so if we take a look here, delta x, or displacement, is the change in the y-axis, and delta t, which is the change in the x-axis. Essentially what you get is, hidden within there is the formula for slope. Whoa. Okay, so you might have heard your math teacher say this is like your rise, right? Your rise over your run. Okay, and so the change in the y over the change in x, we have the slope formula of y2 minus y1 all over x2 minus x1, and that is the same as saying x final minus x initial over t final minus t initial. Okay, and so all of this being said, for this is one of your important notes. So important. I'm gonna put a little star after I write it over here. I'll do a little rainbow star, right? Very important. For a position time graph, slope is velocity. Okay, and we saw that right here. Your slope is your velocity. All right, and the way that we know that is we have to take a look at two things. We have to take a look at the y-axis variable, which in this case it was position, and we have to take a look at the x-axis variable. In this case, it was time, right? And if we divide position over time, what we get is the formula for velocity. So that's how we know that the slope for a position time graph does in fact give you velocity. So let's go back to these 1 second and this 3 second mark. So if we take a look at the 1 second, 3 second mark, I'll do this in a different color ink. Okay, we know that it's a slope. So if I create a secant line, right? Try to make this as straight as possible. Ooh, there we go. So the slope of that line, okay, we already figured it out before, is 8 meters per second. Is that fascinating? I can even see that the units line up. Rise, which is meters, and seconds, which is the run. All right. So what this tells us is that this secant line, so we're adding to our list of very important information. If the slope is the velocity, then average velocity is the secant line. Okay. Double star that one. So very important. Okay. The average velocity is the secant line. All right. So you can see the average velocity for any two points. So for example, I'll do this in red, right? Let's say we're looking at t of 0 seconds and t of 4 seconds, right? What would that look like? Well, 0 seconds is right there, and let's just pretend that 4 seconds is right there. All you gotta do is create a secant line. Boom. Okay, and whatever slope that is will be your V average between these two time intervals. Okay, and we can even shrink those time intervals down just to make a point. Let's say we go from here to here, right? The secant line that cuts right through, right? The slope is the average velocity. All right, cool. Let's go to the next idea. All right. So let's say instead of a position time function, you're given a velocity function. So what this velocity function tells us is that as time progresses, your velocity is changing. Ooh, big important ideas here. So let's create a quick table, right? So V and T. Whenever you create a table, important, give yourself units. So at time 0 seconds, your velocity is 0 meters per second. At time 1 second, your velocity is 4 meters per second. And then let's just do one more. At time 2 seconds, your velocity is 8 meters per second. So a couple of very important ideas. Now we're rehashing our knowledge. Okay, so your velocity is changing. And remember what we said, because the velocity is changing over a period of time, we have acceleration. So what we're looking at is accelerated motion. And as a reminder of a definition, we have acceleration when your velocity changes, all right? So if we analyze this, and if I were to do a quick graph, once again, focusing on quadrant 1, I'm going to make sure I have correct units. So the y-axis is going to be velocity, and your x-axis is going to be time, like so. Okay, our line is going to look something like this. Boom. All right. So this line is described by that function right there. Okay. Now, there's a couple of things that we can tell from this formula. Okay. So let's reuse the skill that we just learned from the previous slide. We said if we're looking at the slope, right? Slope, what you have to do is you have to take your y-axis variable, and in this case, we have the change in velocity, okay, over your x-axis variable, which is the change in time. And you have to find a formula that is associated with that right there. And we know that the change of velocity over the change in time, well, I hope you guessed it, the slope is your acceleration. So if we take a look at this graph, we can see that the velocity is changing according to this table here. For every 1 second that passes, your velocity changes by a factor of 4. So your slope, which is your acceleration, is 4 meters per second for every second, right? And that is your acceleration. Okay, so we reuse the skill that we just learned, right? In order to find what does the slope represent, all you have to do is put the formula in rise over run, change in y-axis over change in x-axis, and try to find a formula that matches it. Okay, so now I'm going to show you secondary skill number 2, right? Your second skill. There's this new skill called area under the curve, okay? And you'll often see me shorthanded as AUC, all right? Area under the curve. So don't get thrown off by the term curve, right? So curve is anything that looks like this or looks like this, right? Those are all curves. But in terms of math and geometry, a line is also a curve. Okay, so here we have a straight line. So because we have a straight line, we can determine the area under the curve. And this is the skill that we're going to do. So from the curve, okay, you're going to create, let's say we're looking from, we'll do something simple at first, from time of 0 seconds. And let's say right here, this is a time of 2 seconds. Okay, you're going to try, just like what I did, is you're going to try to create a shape. So at the 2 second mark, I'm going to create a dotted line all the way until the x-axis. And the shape that you get between the curve and the x-axis, okay, that is our area under the curve. And the term area is literally just that. It's the area. So we take a look at the shape, right? I'm like, oh, that's a triangle. I gotta find the area of a triangle. Okay, so let's break this down. We know that the base of this triangle, is total of 2, and the rise of this triangle, or the height of this triangle, right, according to our table, at 2 seconds, this is 8 meters per second right there. So this is 8. So if I use my triangle formula, I'm gonna scroll this down a little bit. We know that the area of a triangle, area is equal to 1/2 base times height, 1/2 times 2 times 8. So the area is going to be 8 meters. Okay, so we just found the area. And you might have noticed I kind of snuck in the meaning behind area in the curve, which is meters. So you might be thinking, okay, well, how did you know that? Well, I'm the teacher here, but I was getting a little ahead of myself. This is how you can tell what the area under the curve represents. And once again, this is one of those things that in your calculus classes, they're going to give you a different skill set to make sure that you understand how to approach this in calculus, but this is how we're going to start off in physics. We're going to integrate the calculus into it. So area, what we did is we multiplied the base, which is the x-axis. So area is the x-axis times the height, which is the y-axis. Okay, so if the formula for area is always going to be base times height, okay, what we are going to do now, just like what we did with the slope formula, okay, we're going to reinsert our formula or our variables for the x and the y-axis. And for the x-axis, it was time, okay, and the y-axis, it was velocity, right? And so you got to be thinking to yourself, all right, well, the area is times velocity, or velocity times time. We haven't seen a formula like that before, right? Exactly. But we actually did. So we know that velocity is the change in position over the change in time. Ooh, are you seeing what I'm seeing? If we move this denominator over here to the other side, what we get is delta x is velocity times the change in time, which matches up with what we just discussed over here. So you can rearrange the formulas that are given to you to see, to find other variables. So in this case, okay, if we rearrange the velocity formula, we find that when we multiply velocity times time, what we end up with is displacement. So what that means is that this area under the curve that we found over here, this area under the curve, represents the object's total displacement for a total of 2 seconds. So I'm going to actually write that down. So we can say the area under the curve is 8 meters, right? And it's just positive 8 meters. That's it. All right, so let's get a quick practice in with different kinds of area under the curves that you'll see. Okay, so I just want to show you different kinds of shapes. Now for this one, I'm going to draw the first quadrant and the fourth quadrant right here, right? So let's say we have, let's say we have this, and then we're going to go up and down like this. And then we're going to actually have a jump like this. Okay, so what I'm going to do is I'm going to label this into the different parts. So let's do part 1. So part 1 is actually going to go from here to here. Now, remember, area under the curve, technique. What you want to do is you want to go from the curve, which is the line, and you want to go to the x-axis. Now, what I see here are two shapes, right? I see a rectangle and a triangle, or a parallelogram, if you know the formula for that. But in order to find the area in the curve, I would find the area of this rectangle first, and then add it to this area of this triangle. Okay, unless you know the formula for a parallelogram, and that'll be your first area under the curve. So I went from the curve, and I drew, and I just shaded it in. Okay, I just shaded in to the x-axis. Now, if you're wondering, Mr. Lee, should I start shading it in? And the answer is yes. Like if you have a paper format, that's exactly what I would do. Right? If you're doing it in your notebook, shade that area. Get in that habit. It really helps. And then we see the next portion. Okay, and this is something new. So I'm going to do this here. We're going to go from the curve to the x-axis. And so this line is the curve, and we're going to shade it into the x-axis. And once again, we have the dual shapes. We have the triangle, and we have the rectangle. Okay. Now, this is unique. Because this is below the x-axis, this area under the curve is negative compared to before, where because this area under the curve is above the x-axis, this area under the curve is positive. Okay, and now we have a unique situation where we have this jump. So because we have a jump, sometimes they'll, if they're nice, they'll just draw a dotted line there. Okay, so that jump doesn't tell us anything. Okay, it just shows you that there was a sudden shift. And so because there was a sudden shift, the technique is still the same, right? We go from the curve and we go to the x-axis, right? And so this area under the curve would in fact be positive. So if you're looking for, for example, if this is a velocity time graph and the question says, what is the total displacement? So total displacement, what you would do is you would add the area under the curve from part 1 to the area under the curve from part 2. Mind you, this is negative, right? To the area under the curve from part 3. And then whatever that numerical value would be is your total area under the curve. It might be positive, it might be negative. And if it's negative, it just simply means that you're going to the left or south, right? Or left or down. All right. Once again, we'll get a lot of practice with this in class. But until then, see you later. Bye-bye.